Hello everyone, welcome back. In this video, we'll be taking a look at the density of the rationals and the irrationals. So, the density of the rationals, well, this basically says that for every rational number for every real number a less than b, there exists a rational number between them satisfying this interval. So, for example, let's do a proof of this. Let's see if this is true. Let's try prove it. So let's see this number line. So this theorem basically is saying that between two real numbers a b, we can always find a rational number such as m over n, because rationals are, remember, can be expressed in terms of fractions. So let's take a proof of this. So let's do the proof of this. So I'm going to start this way: 1 over n, 2 over n, 3 over n, and so on and so forth until I reach the interval. So the idea is that we take a small enough rational number, 1 over n, that we end up in the interval ab. Note that the spacing 1 over n should be sufficiently fine so that we're guaranteed to pass through this interval AB. Note that if 1 over n is big, we'll just skip the interval. For example, let's go for a different color there. We'll go from here to here to here directly. We'll skip the interval. So we have to make sure the spacing is fine enough, such as this way, such that we're always guaranteed to pass through the interval. So there's a m over n at one point. So let's do the proof of this. So we're gonna say choose any n, choose an n such that 1 over n is less than b minus a. In that way, we're guaranteed to pass through the interval if 1 over n is greater than b minus a, if 1 over n is greater than the distance between a and b, we're going to skip the interval. So choose an n such that 1 over n is less than b minus a. So this can also be written as 1 is less than bn minus an. Oh, I'm sorry, bn minus an. So remember that we're trying to find a rational number between a and b. So this can be written as an is less than m is less than bn. Alright, so now choose m. So we have to show that we can find an m that is greater than an and that is less than bn. So we're going to say choose m to be the smallest integer greater than an. So for example, if an is 3.2, then the smallest integer greater than 3.2 is 4. So choose n to be the smallest integer greater than an. If an is 5, then m should be 6. It's because 6 is the smallest integer greater than an, which is 6. So that's just an example. It's not really 6. So now we need to show, since we're already shown that, since we're already choosing this, we have to show that m is now less than bn. Now we need to show, remember, it's always good to write down what we need to show when we're doing proofs. We need to show m is less than bn. Since m is smallest integer greater than an, then by subtracting 1 we get m minus 1 should be, of course, less than an. for example, an is 3.2, and if then we choose m to be 4 because that's the smallest integer greater than 3.2, then 4 minus 1 will of course be less than or equal to an. So we're going to subtract 1 from an. So this can also be is the same as m plus m being less than or equal to an plus 1. And remember, from right here, from this equation we got right here, this is the same as 1 plus an less than bn. And since an plus 1 is less than bn, and m is less than a or equal to n plus 1, which is less than bn, we have showed that m is less than bn because m is certainly less than an plus 1, and an plus 1 is certainly less than bn. So m is less than bn. So we've showed the inequality, we've shown this inequality, we've shown this inequality. So this is true. Therefore, we're done with the proof. So this is an interesting proof. So although the real numbers is it's a bigger subset, it's a bigger set than the rationals, and the rationals is a subset of the real numbers. There's always a rational number between any two real numbers, and just like that, there's always an irrational number between any two real numbers. So the proof of this is pretty much the same. So consider this: we have to show there's a irrational number b between the real numbers a plus b. So let's shift the. So I'm not gonna do the full proof. You guys, I'm gonna sketch it out. You guys can do it formally for practice. So I'm gonna add root 2 to a and b. So we're just basically shifting what we had by root 2. Right. So now I'm just gonna subtract root 2. So we are gonna end up with, and p minus root 2 is certainly uh, an irrational number, because rational minus irrational is a irrational. So I'm using the previous theorem to try to help us prove this theorem. So we had a rational number p between a and b. So I've shifted it by root 2. I've shifted the interval by root 2, and I've subtracted by negative root 2, and we get a rational minus irrational, which is irrational. So we get that this irrational number also exists between these two real numbers. So we're just shown that between any two real numbers, there always exists a rational number and an irrational number. So hope you guys enjoyed the video. See you next time.